My name is Panchala Srinivas from Tribly branch, roll number 23951A02223A section. Subject Essentials of Problem Solving. Topic Graph Terminology, Concepts and Applications in a Computer Science. Graph Terminology, Concepts and Applications in a Computer Science. A graph theory is a fundamental branch of mathematics of computer science that deals with the study of graphs. Mathematical structures are used to model precise relationship between objects. Understanding the key concepts and terminology associated with graphs is essential for students and professionals working in the field of computer science. Graphs have a wide range of applications from social network analysis, analysis and recommendation systems, route planning and optimization algorithms. Nodes and edges. Nodes, edges, adjacency. Nodes, also known as vertices. Nodes represents the individual objects or entities in a graph. Node can represent a variety of things such as people in a social network, web page in a hyperlink structure, or a airport in a transportation network. Edges. Edges also called links or connections. Represents the relationships or interactions between the nodes in a graph. Edges can be directed, indicating one-way relationships, or undirected, indicating two-way relationships. Adjacency. Two nodes are considered adjacent if they are directly connected by an edge. The set of nodes are there adjacent to a given node are referred to as its neighbors. Graph representations. Adjacent matrix, a 2D array that represents the connections between nodes in a graph. Each row and column corresponds to a node, and the value in each cell indicates whether there is a edge between the corresponding nodes. Adjacent list, a collection of a linked list where each list represents the neighbors of a node. This representation is often more efficient for spacecrafts where most nodes are not connected. Edge list, a simple list of all the edges in the graph, typically represented as a collection of node pairs. The representation is useful for operations that involve iterating over all the edges in the graph. Incidence matrix, a matrix that represents the relationship between nodes and the edges in a graph. Each row corresponds to a node and each column corresponds to an edge with value of indicating the connections. Graph properties. Directed versus undirected. Graph can be either directed where the graphs have specific directions or undirected whether the edges have no interaction direction. Weighted versus unweighted. Edges in a graph can be have associated weights or chords which can represent force factors like distance, time and importance. Unweighted graphs have edges with no associated weights. Cyclic versus acyclic. A graph is cyclic if it contains at least one cycle where a sequence of edges can be followed to return to the starting node. A cyclic graph such as trees do not contain any cycles. Connected versus disconnected. A graph is connected if R is a path between any two nodes, where a disconnected graph contains multiple independent components that are not connected. Graph traversal algorithms. Breadth first search (BFS). BFS is an algorithm that explores a graph by visiting all the neighbors nodes at the present depth before moving on into the nodes at the next depth level. It is often used to find the shortest path between two nodes in an unweighted graph. Depth first search (DFS). DFS is an algorithm that explores a graph by going as deep as possible as each branch of backtracking. It is often used to find a path between two nodes or to direct cycles in a graph. Dijkstra's algorithm. Dijkstra's algorithm is used to find the shortest path between two nodes in a weighted graph. It is works by iteratively selecting the node with the smallest distance from the source node and updating the distance of its neighbors. Graph applications. Social network techniques. Graph are used to find model social where node are represent users and edges represent connections or relations between graph. Analysis can reveal insights about influence users, communities, and information flow. Route planning. Graphs can model transportation networks where node represents the locations and its presentation routes or flight routes. Graph algorithms like Dijkstra's can be used to find the shortest or most efficient routes between locations. Recommendation system. Graphs can model the relations between items such as products or contents that uses graph algorithms to make personalized recommendations to user based on their interests and behaviors. Circuit designs. Graphs can model the connections between components in electric circuits, allowing further analysis and optimizing of the circuits design using graph-based algorithms. Graph algorithms and complexity. The time complexity of the graph algorithms refers to how the running time of the algorithm scales the size of the input graph. Understanding the complexity is crucial for selecting the most efficient algorithm given problem. Space complexity. The space complexity of the graph algorithm to the amount of memory required to run the algorithm, which is particularly important for the large graph set that it may not fit entirely in memory. Algorithm optimization. Graph algorithm can be optimized by leveraging the properties of graphs such as sparsity of the presence of certain structure to reduce the time and space complexity. Graph concepts. Isomorphism. A property where two graphs have the same structure even if they have different nodes or eligible edge labels. Bipartite graphs. Graphs where the nodes can be divided into two disjoint sets and edges only exist between nodes in different sets. Planar graphs. Graphs that can be drawn on a plane without any edges crossing each other. Minimum spanning tree. The subset of edges weighted graph that connected all the nodes at the have the minimum total weight. Graph theory in the real world. Transportation networks. The graph can model transportation networks such as road system, airline routes, and rail networks, allowing for the optimization of travel routes, scheduling, and infrastructural planning. Social media analysis. Graph can represent social networks where no nodes are used and edges are connect, connections, enabling the analysis of user influence, information propagation, and community structure. Biological systems. Graphs can model biological systems such as protein interaction networks and neural networks, providing insights to the complex relationships and dynamics within these systems. Thank you.